In previous chapter, we have discussed about different aspects related to raster data modeling. In this chapter, we will discuss about the vector data model, different formats in vector model, vector data model structures, advantages and disadvantages of vector model, and comparison between raster and vector model. In contrast to the raster data model, the vector data model is present. In this model, the space is not quantized into discrete grid cells like raster model. Vector data models use points and their associated x and y coordinate pairs to represent the vertices of a spatial feature, much as if they were being drawn on a map by hand. The data attributes of these features are then stored in a separate database management system. The spatial information and attribute information for these models are linked via a simple identification number that is given to each feature in a map. Three fundamental vector types exist in geographic information system: points, lines and polygons. Points are zero-dimensional objects that contain only a single coordinate pair. Points are typically used to model singular discrete features such as buildings, wells, power pole, sample location and so forth. Points have only the property of location. Other type of point features include node and vertex. Specifically, a point is a standalone feature, while a node is a topological junction representing a common x and y coordinate pair between the intersecting lines or polygons. Vertices are defined as each bend along a line or the polygon feature that is not intersecting of lines or polygon. In the following figure, you can observe the points have been present, the bending of the lines can be seen and the polygons have been represented. You can see that the point location are the intersection junctions that are being present, whereas the lines are nothing but the roadways or it might be a railways that is been passing by. Whereas the polygon features you might have seen the vertices are being present. Points can be spatially linked to form more complex feature. Lines are one-dimensional features composed of multiple explicitly connected points. Lines are used to represent linear features such as roads, streams, falls, boundaries and so forth. Lines have the property of length. Lines that directly connect two nodes are sometimes referred to as chains, edges, segments or arcs. Polygons. Polygons are two-dimensional features created by multiple lines that loop back to create a closed feature. In the case of polygon, the first coordinate pair or the point on the first line segment is the same as the last coordinate pair on the last line segment. Polygons are used to represent features such as city boundaries, geologic formations, lakes, soil association, vegetation community and so forth. Polygons have the property of an area and perimeter. Polygons are also called as areas. Vector data formats. The vector data model is only a general strategy for representing objects. They are dozens of physical data structure that is nothing but the file format that is being present and that organized vector geometry and attributes in different ways with unique capabilities. For example, some formats are able to store topology while others cannot. Some formats store the geometry and attributes in separate files while others, typically called as spatial database, store the geometry as one column in an attribute table. The following are the examples for the data files. Shapefile. Shapefile is being used by ESRI. Geodatabase feature class, it is being again used by ESRI. GML is used in OpenGIS Consortium. KML is being used by Google. GeoDSN is being used commonly. Non-GIS graphical software including CAD and drawing programs such as Adobe Illustrator are also based on vector models. Vector data model structures. Vector data models can be structured in many different ways. The simplest vector data structure is called the spaghetti data model. In the spaghetti model, each point, line or polygon feature is represented by a string of x and y coordinate pairs, or as a single x and y coordinate pair in the case of a vector image with a single point with no inherent structures. One could envision each line in this model to be a single strand of spaghetti, that is, formed into complex shape by the addition of more strands of spaghetti. It is notable that in this model, any polygon that lie adjacent to each other must be made up of their own lines or strands of spaghetti. In other words, each polygon must be uniquely defined by its own set of x and y coordinate pair, even if the adjacent polygon share this exact same boundary information. This creates some redundancies within the data model and therefore reduces efficiency. The following is an image that is being shown how the spaghetti model is being used. We can observe that the number of lines and the area is being represented in the form of lines, and each point is being given as a connectivity. Despite the location designation associated with each line or strand of spaghetti, spatial relationships are not explicitly encoded within the spaghetti model. Rather, they are implied by their location. This results in lack of topological information, which is problematic if the user attempts to make measurements or analysis. The computational requirements, therefore, are very steep if any advanced analytical technique are employed on vector file structure thusly. Nevertheless, the simple structure of the spaghetti data model allows for efficient reproduction of maps and graphics, as this topological information is unnecessary for plotting and printing. Topological model. In contrast to the spaghetti data model, the topological data model is characterized by inclusion of topological information within the data set, as the name implies. The topology is a set of rules that models the relationships between the neighboring points or lines and polygon and determines how they share the geometry. Topology is also concerned with preserving spatial properties when the forms are bent, stretched or placed under similar geometric transformations, which allows for more efficient projection and reprojection of map files. Three basic topological percepts that are necessary to understand the topological data model are outlined. Firstly, connectivity describes the arc node topology for the feature data set. As discussed previously, nodes are more than simple points. In the topological data model, nodes are the intersection points where two or more arcs meet. Arc node topology. In this case, the arc node topology, arcs have both a form, that is node, that is nothing but the starting node, indicating where the arc begins, to a two node, that is the end node, that is nothing but a starting node, the ending node, and we have an arc here. In addition, between each node pair is a line segment, sometimes called a link, which has its own identification number and reference both its from node and to node. In the figure where the arc node topology is being expressed, where arc 1, arc 2 and arc 3 all intersect because they share the node 11. Therefore, the computer can determine that it is possible to move along arc 1 and return into the arc 3, while it is not possible to move from arc 1 to arc 5, as they do not share a common node. In this figure, you can travel from one node to another node in the form of arc if they are connected. Sometimes the nodes are not being connected by the arcs. So, in such situation, it is being difficult. So, this also gives us a basic understanding about the connectivity in the topology. Polygon arc topology. The second basic topological percept is area definition. area definition states that arc that connects to surround an area defined a polygon, also called polygon arc topology. In the case of polygon arc topology, arcs are used to construct polygons and each arc is stored only once. The figure is been describing the polygon arc topology. This results in a reduction in the amount of data stored and ensures that adjacent polygon boundaries do not overlap. In the image, you can see different areas have been denoted by B, C, D, E, F, where each area is being represented by what number of arcs or what number of arcs are been determining that particular polygon area. Polygon topology. Contiguity. The third topological percept is based on the concept that polygons that share a boundary are deemed adjacent. Specifically, polygon topology requires that all arcs in a polygon have a direction, a from node to a to node, which allows adjacency information to be determined. The polygon that shares an arc are deemed adjacent or contiguous, and therefore, the left to right side of an each arc can be defined. This left to right polygon information is stored explicitly within the attribute information of the topological data model. The universe polygon is an essential component of polygon topology that represents the external area located outside of the study area. The figure shows the polygon topology where the arc sec is bound on the left by polygon B and the right by polygon C. Polygon A, the universe polygon, is to the left of arcs 1, 2 and 3. So, in the table you can easily observe that what number of arcs is being present and what type of polygons have been adjacent to that arcs. So, 1 is where we have the two polygons A and B are being adjacent. The similar way we have 2 where we have C and A are being adjacent to that arcs. Common topological errors. Topology allows the computer to rapidly determine and analyze the spatial relationships of all its included feature. In addition, topological information is important because it allows for efficient error detection within the vector dataset. In the case of polygon feature, open polygon or closed polygon which occur when an arc does not completely loop back upon itself, and unlabeled polygons which occur when an area does not contain any attribute information. Violate polygon arc topology rules. Another topological error found with polygon feature is the sliver. Slivers occur when the shared boundary of two polygons do not meet exactly. In the case of line feature, topological errors occur when two lines do not meet perfectly at a node. This error is called an undershoot, when the lines do not extend far enough to meet each other, and an overshoot when the line extends beyond the feature. For example, you have line A and line B. Whenever, and this is a point, whenever we have the lines are not being intersecting and there is a gap between the two lines, it is called undershoot. Whereas, whenever there is an extension of the lines have been seen, then we have overshoots. Undershoot is an dangling node at the end of the line. Dangling nodes are not always an error, however, as they occur in the case of dead end streets on the road map. So, you can see different types of overlay, underlay and types found in the image where two points are not joining. There we have the overshoot, then we have undershoot that has been present. Many types of spatial analysis require the degree of organization offered by topological explicit data models, in particular network analysis, which is used in finding the best route from one location to other, and measurement. Example, finding the length of the river segment relies heavily on the concept of to and from nodes and uses this information along with attribute information to calculate distances, shortest route, quickest routes and so forth. Topology also allows for sophisticated neighborhood analysis such as determining adjacency, clustering, nearest neighborhood and so forth. Now, that the basics of the concepts of topology have been outlined, we can begin to better understand the topological data model. In this model, the node acts as more than just a simple point along a line or a polygon. The node represents the point of intersecting of two or more arcs. Arcs may or may not loop into a polygon. Regardless, all nodes, arcs and polygons are individually numbered. This numbering allows for quick and easy reference within the data model. Advantages and disadvantages of vector model. In comparison with the raster data model, vector data models tend to be better representation of reality due to the accuracy and precision of points, lines and polygons over the regularly spaced grids of the raster model. This results in vector data tending to be more artistically pleasing than raster data. Vector data also provides an increased ability to alter the scale of observation and analysis. Each such coordinate pair associated with point, line and polygon represent an infinitesimally exact location, albeit limited by the number of significant digits and or data acquisition methodologies. Zooming deep into a vector image does not change the view of the vector graphic in the way that it does for a raster graphic. Vector data tend to be more compact in data structure. So, file sizes are typically much smaller than their raster counterparts. Although the ability of modern computers has minimized the importance of maintaining small file sizes, vector data often require a fraction of computer storage space when compared to the raster data. The final advantage of the vector data is that topology is inherent in the vector model. This topological information results in simplified spatial analysis, for example, error detection, network analysis, proximity analysis and spatial transformation when using a vector model. Alternatively, there are two primary disadvantages of the vector data model. First, the data structure tends to be more complex than the simple raster model. As the location of each vertex must be stored explicitly in the model, there is no shortcuts for storing data like there is the raster model. Example, the run length, the quadratary encoding methodologies. Second, the implementation of the spatial analysis can also be relatively complicated due to the minor differences in accuracy and precision between the input data sets. Similarly, the algorithm for manipulating and analyzing vector data are complex and can lead to intensive processing requirements, particularly when dealing with large data sets. Comparison of raster and vector data models. The question often arises, which is better, raster or vector data models? The answer is neither and both. Neither of the two classes of data model are better in all conditions or for all data. Both have advantages and disadvantages relative to each other and to additional more complex data models. In some instances, it is preferable to maintain data in raster model and others in the vector model. Most data may be represented in both and may be converted among the data models. As an example, elevation may be represented as a set of contour lines in the vector data set or as a set of elevation in a raster grid. The choice often depends on the number of factors, including the predominant type of data, whether it is a discrete data or it is a continuous data, the expected types of analysis, availability of storage, the main source of input data and the expertise of the human operators. Raster data model exhibit several advantages relative to the vector data model. First, raster data model are particularly suitable for representing themes or phenomena that change frequently in space. Each raster cell may contain a value different than its neighbors. Thus, trends as well as more rapid variability may be represented. Raster data sets are generally simpler, particularly when a fixed cell size is used. Most raster models store cells as set of rows with cell organized from left to right and rows stored from top to bottom. This organization is quite easy to code in an array structure in most computer languages. Raster data model also facilitates easy overlays, at least relative to vector model. Each raster cell in a layer occupies a given position corresponding to given location on the earth's surface. Data in different layer align to cell over this position. Thus, overlay involves locating the desired grid cell in each data layer and comparing the values found in the given location. This cell lookup is quite rapid in most raster data structure, and hence layer overlay is quite simple and rapid when using a raster data model. Finally, raster data structure are the most practical method for storing, displaying and manipulating digital data such as the aerial photographs, the satellite imagery. Digital image data are important source of information when building, viewing and analyzing spatial database. Image display and analysis are based on raster operation to sharpen details on the image, specify the brightness, contrast and colors of display and to aid in the extraction of information. Vector data models provide some advantages relative to raster data model. First, vector model generally lead to more compact data storage, particularly for discrete objects. Large homogeneous regions are recorded by the coordinate boundaries in a vector data model. These regions are recorded as a set of cells in a raster data model. The perimeter grows more slowly than the area for most feature shapes. So, the amount of data required to represent an area increases much more rapidly with a raster data model. Vector data are much more compact than the raster data for most themes and levels of spatial detail. Vector data are more natural means for representing connectivity and other connected linear features. Vector data by their nature store information on the intersecting nodes and the linkage between them or the lines linkage, traffic volume, speed, timing and other factors may be associated with lines and intersection to model may kind of networks. Vector data model are easily presented in preferred map format. Humans are familiar with continuous line and rounded curve representation in hand or machine drawn maps, and vector based maps show these curves. Raster data often show a stair step edge for curved boundaries, particularly when the cell resolution is large relative to the resolution at which the raster is displayed. Cell edges are often visible for lines, and the width and the stair step pattern changes as the line curves. Vector data models facilitate the calculation and storage of topological information. Topological information aids in performing adjacency, connectivity and other analysis in an efficient manner. Topological information also allows some forms of automated error and ambiguity detection, leading to improved data quality. Summary: the real world around us is not uniform and smooth. The data models provide a way of visualizing and researching about the world in an organized and structured way in a digital domain. A geographic model is an abstract and well-defined system of concepts and respective vocabulary to describe and reason about real world. The object-based spatial database, those obtained by field surveying, remote sensing, image analysis, photo interpretation and digitization, etc., are generally represented in the form of coordinated lines and termed as vector data model. When the spatial data is structured on the field based model, the basic spatial units are different from the tessellation, that is nothing but regular as DEM or irregular as STIN, are termed as raster data model. Images from remote sensing, scanned map, etc., are all in the raster format. whereas census data, that is the tabular data, the US census, the DLG form, USGS for streams, roads, etc. are all vector data. Raster data model are best for continuous feature including elevation, temperature, soil type, land use, etc. whereas best for features with discrete boundaries like property lines, transportation, political boundaries are vector data models.